So welcome to the session here, and you've probably seen where we have the videos from the different lectures. I mean, the quality of the videos is so and so because it's just a raw dump of what we are doing. But what I wanted to quickly bring up now is this discussion we had last week, last Monday, about linear regression and logistic regression. So we are entering the domain of classification problems. Till last Monday, we've been looking mainly at us trying to fit a continuous function. And these kind of methods, logistic regression methods, they can actually be used now for classification problems, whether we have a classification problem with a binary class, which means true, false, 1, 0, bad, good, whatever, or we can have many more classes or categories. Now, the classification problems are actually some of the most common ones we have in machine learning. And typically, if you think of image classification, or if you guys are running an experiment and you have an image from the detector, you have different types of events. It could be a proton event, it could be a carbon atom, it could be an alpha particle coming out. Then you have ways to trace this in the detector. And that means that you often deal with images. And you can then train a machine learning algorithm to recognize these images. So this is often done in nuclear physics. There are many cases where people have used machine learning algorithms to classify specific types of events. So you can train that. And as you train images of cats, dogs, houses, cars, etc. So that is a typical application of some of these classification methods. And I see now that my screen is really playing a bad role here. We would have to figure out why this is so flaky. Okay, so the thing which we did last time was then to look at some of these examples with classification. And when we run this code here, which is about coronary heart disease, and what we saw then when we plotted it, if we now looked at the number of patients who got coronary heart disease as a function of given age, we see very clearly that in this case, we are classifying this as 1 or 0. So 1 is the bad case, which means that you actually do get a heart disease, whereas the 0 here is classified as not having a heart disease. And in this specific case, if you were to fit a straight line, you could actually fit a line which divides the two. And then you could say that if the value is above 0.5, then you have a output equal to 1. Or if it's below 0.5, you would classify that as a 0. But clearly fitting a function to this data becomes difficult. If you want to fit a polynomial, you could fit a very complex polynomial which goes through the data, but then your predictive power would be pretty low when you go to other cases. So when you plot that, test that on test data. And in this case, what we did was to plot the mean values, and that has a form as an S shape. And this is something which then we could think of as a kind of way to classify the data. So if the value of this function is below 0.5, we give an output 0, and else we give an output 1. And then what we did then was to introduce this logistic function, which plays the role of a probability. So there are many such functions which are being used, but the logistic function is a very convenient one, because when this argument t goes to -infinity, it goes to 0. And when the argument t becomes large, it goes to +1. So then what you would say, if you generate a value p of t, you would then typically say that if that value is below 0.5, then you classify this as 0, or true, or false, or whatever you do. And then if it's 1, if it's above 0.5, you would classify it as a 1, or a true case, or something similar. And as we discussed last time, there are different types of functions which we can use then to actually perform this kind of fitting. And we could have the sigmoid function, we would like to avoid the step function because it has a discontinuous derivative. And this is also something to keep in mind when we are moving to neural networks. Because in neural networks, these functions are going to play the role of activation functions in hidden layers. And we are going to call these functions many, many times, and also their derivatives. And you don't want to have derivatives which are discontinuous, and you want to have derivatives which are easy to calculate numerically, which don't require too many floating point operations. Similarly, there's a tanh function, which is also very much used. And when we went through this last time, we made an assumption that we want the maximum likelihood. We assume that every single event y is independent of the other ones, and it is identically distributed. So then we construct a probability distribution, which is a product of all the single probabilities, and we use the binomial distribution, and then we want to maximize this quantity. And then when we maximize this quantity, we ended up with these two expressions. So I'm just repeating what we did last Monday. So you can extend this to more predictors or features, many different names for the same quantity. So if we are looking at this cancer data from Wisconsin, which is a very popular data set, there are 30 features in total. One of the features is the mean squared radius, the mean area, etc., etc. And so these features have a meaning for pathologists when they are classifying tumors. Now, one of the things we did then was actually to, let me bring up this one. So this would be the, not that one. I'm just gonna bring up the Wisconsin cancer data. So this is a data set, and I'm gonna run logistic regression on that one. And this data set is an interesting one because it has lots of features which can then be used in training. And the data set is included with scikit-learn. So we will simply load it like this. And then here's a plain logistic regression. And this LBFGS, as we discussed last time, stands for Broydens, Farberg, and the two other names I never remember. And it's a Quasi-Newton method, and we are going to see what that means in just a few moments. And we split the data. So this solves logistic regression, and it does a classification. It solves the data by splitting in test and train, 80% for training and 20% for testing. And the test accuracy, which is the sum of all the events which have been classified correctly, divided by the total number of events. This is something which here pops out as 0.94, which is okay. So this means 94% correct classification. Now, there's something I wanted to say as a digression, and I don't remember if I emphasized that last time. But when you look at data, there's something which is extremely useful to look at. So if you remember back to the definition we had of the covariance, so the covariance measures the correlations among different features. So here you have 30 features. And in scikit-learn and using pandas as well, you can display these things easily. Another thing you can display here is a histogram of the benign tumors and the malignant ones. And you can actually look at how many are classified as, if you look at this one, you can now see how many are classified as bad ones and the good ones. And you see that for the mean radius, when you have a small mean radius, this is just a histogram of the frequency of tumors. And this frequency here simply tells you how many bad cases you have and how many good cases you have. You see that there is a preponderance of benign cases. So that also makes a problem when we are doing classifications because you have more of one data set. But you see clearly that the mean radius and also the mean area seem to have a similar behavior, which is expected. If you think of the area of the tumor as a circle, then clearly the area has to be proportional with the mean radius. And you see also the mean perimeter there seems to be a very strong correlation there with the mean radius and the mean area. There are other things which I don't know what mean, because I'm not a specialist in medicine. So we would have to ask a pathologist, what does this actually mean? And these are features, these are the 30 features which are often listed. But for us, another interesting thing is actually the correlation matrix, which is the same as a covariance matrix divided by the variance. That means that you have 1 along the diagonals. But you see here that the mean radius, if you have a value of 1 or -1, that means strong correlations. And clearly the mean radius and the mean area, as we would saw intuitively, and we would guess that that's the case, are strongly correlated. So if you were to do a linear regression here and set up your design matrix and try to invert that one, you would get a determinant which is 0. Because you would have in each column of the design matrix, you would have quantities which are strongly correlated with each other. When you calculate the covariance matrix and thereafter the correlation matrix, you can actually extract very quickly a feeling of which data are more correlated or not. So there's another thing which you may have heard of, and that's called the principal component analysis, which we may discuss a little bit later. So the principal component analysis is based on you diagonalizing this matrix. When you diagonalize this matrix, you get the variance. So that diagonalizing means you have an orthogonal transformation where your matrix becomes diagonal. And what you can do then is to say that there are specific features which have a large variance, and I will keep those, and I take away those which have a small variance. Doing that means that you're reducing the dimensionality of the problem by looking at those features which you think are the most important ones. So the correlation matrix and the covariance matrix are very interesting properties in machine learning, because this gives you, without having done anything, a quick view on the data. And it tells you which data or which features are correlated with each other and which ones you may expect could be important in the analysis. So diagonalizing that matrix and only keeping the largest eigenvalues, which are exactly the same thing as the variance, means that you would then have a way to reduce the dimensionality of the problem. And that is often done. If you can diagonalize that matrix, suppose you have 10,000 features, you can still diagonalize that. If you want to train a neural network with 10,000 features, then you can just wait and wait till the neural network has done the training, because that will take a lot of time. So you would typically reduce the dimensionality before you start using any of these machine learning methods. And we're coming back to that a little bit later. Hey guys, any questions so far? Don't be shy, eh? We discussed this a little bit last week as well. And then there's another feature which is often used, and that's the so-called confusion matrix. Have you heard of that? Or the error matrix? So when you saw the accuracy we had, what we had was a total accuracy, which was 94 or 95, depending on how we started. But that's a total one of benign cases and bad cases. What you can do, however, is to do something like this. And now I need this analog thing. So you can actually calculate the true positive case. So these are the benign cases. Actually, in the data set, positive means you having a bad tumor, which I think is the opposite, but I think that's the way they are set up. But you see now that you do well on 96% of the cases. This is a false positive, which means that of the positive events, you classify wrongly 4%. This is actually a very easy way to display a classification problem, because it tells you how well you do on the two classes you have. And you can extend this to many categories of classes. So, and this tells you that the true negative, you do well on 93% and you miss 7%. So instead of looking at the total accuracy, which is this number is actually something which is very meaningful, and it conveys results in a more, how to say, intuitive way. And these are quantities with scikit-learn, which you can set up quickly. So there is a package which is called scikit-plot. And the only thing you do now, you make your prediction, you run your fit, and then there is a matrix which is called plot confusion matrix. So confusion matrix is, I think the name is a little bit strange. I like to call it the error matrix. You will also see it being named that. But it's because you don't want to confuse the different cases. So I think that's the root of the name. I like often the error matrix. But you will see also there are other types of ways of plotting these results, which are very popular. One is called receiver operating curve, ROC curve, which tests the true positive rate against the false positive rate. And there are different ways of mixing these type of ways to classify events. But the one which I think is very intuitive, actually many of the other ones I have to rethink all the time. I think this is something which for a simple guy like me actually works pretty well. And that conveys the message about how well your model is doing. So these were just some small digressions. What I want to do now is to bring back where we were last week, and we're going to look at some of the basic optimization algorithms. And the plain easiest one is a gradient descent, which is just a brute force method, and that's often used actually. And then we have stochastic gradient descent and the whole family of methods there. And this is what I was planning to go through. And then we also, I wanted to use, let's say, till 4 today, we take a break. And then after that, I wanted to discuss with you guys more the project, if there are specific things you would like to do. So we can always tailor that to your needs. But you probably have tons of questions because I don't know if you had time to look at the exercises. So when I'm not here and watch over your shoulders, I guess I'm not asking if you've done the exercises or not. There are exercises in every weekly material. And some of these are actually useful for getting started with a project. Okay. And these are things which we can discuss as well. So I would like to propose that we spend some time just together discussing things here. Because just listening through Zoom talks is not the most exciting thing. It's a fun thing, actually. I had a student back in the US who said she liked to listen to the videos because she felt that they had such a calm voice that when she needed to relax, she just put on my videos. Maybe she fell asleep. Okay, guys. So let me just bring up my stuff here. And then I'm going to switch to the whiteboard. Just this way. So the thing we did last week was actually to take this cost function and we took and made a Taylor expansion. So I'm just going to repeat some of the equations which we did last time. So we Taylor expanded the cost function, this C of beta, as function of a small variation around the optimal value minus a beta of n. And this beta of n is a result from the previous iteration. But now you can just think of this as two numbers which are pretty close to each other. So we're actually getting close to the solution where we have dc beta equal to 0. And that is where we find the optimal parameters beta. And what we found then last time is, I'm just repeating the equation we got. We found that this beta hat which we labeled as a beta of iteration n+1, is then given as a beta of n minus, and then we had the inverse of this matrix H, and this is something which now applies to any cost function. So this is not limited to classification. So we can apply this to what we did with ordinary least squares. And actually the exercise at the end of the the material we have deals with us simply implementing this algorithm for a plain polynomial approximation. So this is a general expression, and then this is multiplied with a gradient calculated at the value of beta of n here. So let me just quickly remind you of what these quantities are. So this quantity is a Hessian matrix, and that is the second derivative of the cost function with respect to these parameters beta. And G is just a gradient. And these quantities, when you see this n, that means that they are evaluated at beta of n. So in this iterative process, so what we did in order to achieve this expression was what we made a Taylor expansion and we stopped at second order. So in principle, what we were doing is that we were setting up a function like this, where we have some vector xt times b, and then we had minus 1/2 times x transpose times a matrix x times a matrix A times a vector x. And then when we took df of x, put that one to 0, what we end up with then is a linear algebra problem, which you have seen many, many times. So if you have a quadratic function in these unknown quantities x, which in our case are the unknown quantities beta, then you have a problem which actually can be translated into a standard linear algebra problem. This is the basis for many of these gradient methods, this approximation which you see here. So if you go in a textbook on convex optimization problems and mathematics textbooks, you will often see them starting with a function like this. And now we're going to optimize this function, find the minimum of the function. And methods like gradient descent, conjugate gradient descent, steepest gradient descent, etc., they're actually based on this approximation. So what we did was simply to expand this guy here, the cost function, to the second derivative. And we didn't care about the higher derivatives. And then we end up with this equation here. Now, there's something which I wanted to say a little bit before we move on here. There's some simple mathematics which we can do actually, but let me repeat for logistic regression, just for the sake of completeness. So in logistic regression, this gradient, or as a function of beta, that was given by this design matrix where we have the features multiplied with the probabilities minus the target value y, which we want to reproduce. So this has an analytical expression, but the problem with logistic regression is that if this is the sigmoid function or the logistic function, then there is an implicit dependence on the unknown parameters. We no longer have a linear dependence. So when we did ordinary least squares, we had a linear dependence. And then we were lucky then, because we could find an equation for the unknown parameters beta, which had a simple analytical form in terms of a matrix inversion problem. And then we also had that the second derivative, this Hessian matrix, which we put up as a function of this beta, was then given by the design matrix. Now I have to remind myself about that. Let me just bring it back again here. Yeah, this was given by X, the transpose, times a matrix W, which only had diagonal elements. So this WII was given by the probability P of I of 1 minus P of I. These are the probabilities for a specific event. And it had only non-zero diagonal elements. So these matrix elements, they do all depend implicitly on the value of beta. So there's no longer a nice linear dependence. Now, one of the things we can do then, when we look at these expressions, is to take a slightly different route, because I want to connect this with ways by which we can say something about this parameter which we use to replace the Hessian matrix with. Expand around a beta value. So we do this beta of n. So let me just bring this up here. Beta of n minus a parameter gamma, which is now going to replace this Hessian matrix. So g of n, just remind you of that one, g of n is a function of beta of n. So the thing you're going to meet now, again and again, in all machine learning, is something which is called the learning rate. So this parameter gamma, or eta, or different names, this is normally called the learning rate. And this is a way to simply replace the complicated calculation of this Hessian matrix. So I'm going to repeat these things in many different ways, because this is really the bottleneck of all of machine learning. Now, you can gain some insights about this Hessian matrix in the following way. So if we now expand around this quantity here, what we're doing now is to perform a new Taylor expansion. So we have a beta of n, so this is a vector, and gamma of g of n, which is also a vector. We would rewrite this one. So it's again a Taylor expansion, but now we expand around this parameter gamma. So then we have minus gamma, and then I have g of n transpose, because this is a vector, and then I have g of n, and plus 1/2 gamma squared, and then I have this g of n, this is transposed, and then I have this Hessian matrix. This is the second derivative of g of n. And then we have high order terms. But we are going to drop the high order terms. So we should put an approximation sign here. So what I've done now is to reinsert again, and it sounds a little bit strange because I'm replacing here. So I'm simply assuming that my gradient is multiplied by some kind of constant. But then I have the second derivative. So remember now that this one is the second derivative. And this is a quantity which we obviously don't want to calculate. If I now take the derivative with respect and then we want to drive this to 0. So if I take the derivative with respect to that quantity, and I also, what I'm going to do now is simply to rewrite g of n. I just rewrite that in terms of g, and then I let this Hessian matrix, h of n, I replace that with h. So just to simplify the equations. What I get then, if I take the derivative and drive it to 0, what we find then is that this learning rate is given by g times g So I have now an expression for it. This, what you see here, is parallel. It's actually not so different to a method which is called steepest descent. And we may discuss that a little bit later. Now, if you look at this, so what I have now is an expression for this gamma. So that means that when I'm setting up this algorithm, beta of n, I could actually put in this one, and now I'm putting in the dependencies on iteration n divided by g of t of n, h of n, and g of n, multiplied with g of n, because this is just my gamma. So I could do that. But if you look at what I have here, you see now that I actually have to calculate this matrix H. And this matrix H is a second derivative. It's your Jacobian. Now, the Jacobian itself is something we would avoid to calculate because now in the linear regression case, we have perhaps 20, 30 parameters. That means that this matrix H has dimensionality, let's say 30 times 30. And we could calculate it. So to invert a 30 by 30 matrix is a baby case, computationally. However, when you come to neural networks, you have millions of parameters. And if you have millions of parameters, it means that you're updating millions of these. And you have to invert a million times a million matrix. And you don't want to do that. Now, there's something, maybe this is a signal because it started at the 3 o'clock now. Maybe it's a signal that we should take a break. Yeah? What do you say? Should we take a small break? And then we just stretch legs. And I would actually like to use these breaks to also discuss with you guys. I mean, what kind of topics you would like to do and work on, etc., etc. I'm going to send you later today some of the projects which people worked on last year, because some people had data which they were working on in their thesis work or their projects here at Ghanaian. So if that's the case, then we can always try to tailor things to your interests. Take a small break, is that okay? Yes. Sure. Now, the reason why I took this kind of more simpler case is that this also relates to a very popular method, which is called steepest descent. But what we see here is that we can actually now update this learning rate by calculating this ratio here. Now, this ratio is also a ratio which is interesting because suppose now that this vector G, just let's make an assumption. And this is normally not the case, but you could assume now that this vector G is an eigenvector of H. So that means that you have something like lambda times G. Let's just make that as an assumption, because this is actually related to a mathematical criterion for the convergence of Newton's method. So which I'm just going to say. But you can see, let's assume that this is the case. Now, then we know that G is then an orthogonal basis. So if I take G transpose times G, that's an inner product. I also have H times G in the denominator here. So that means that this becomes just a constant times G. And then I have G transpose times G, an inner product, and an inner product here. So they cancel each other. So what I would have then, if this is the case, what I get is that this beta of n is then simply 1 divided by the eigenvector of this lambda of n times G of n. This has a, sorry, not, that was a little bit wrong what I wrote here. So this beta, we get this expression here. So the next iteration, beta of n plus 1, is equal to this quantity here. But what you see is that at every iteration, you would have to calculate an eigenvalue. There is a convergence criterion, which I'm just stating. So the convergence criterion criterion is that this gamma should be smaller than 2 of the max eigenvalue, where lambda max is the largest eigenvalue of the Hessian matrix. So I'm just stating this result, which you can find in textbooks on convex optimization theory. This means that if there is a big gap between the minimum and the maximum eigenvalues, then these methods can have actually problems in converging. This is also called something which you may have heard about, is called a condition number. So this is the largest eigenvalue. And you can, in the examples which I have, you will see examples where I implement the gradient descent method, where I typically tune this parameter gamma to be the largest eigenvalue. So let's now look at an example on how we could implement this kind of approach here. So the simplest method, which is called gradient descent. So when you see that, this simply means that we have a beta of n plus 1, which is equal to the previous value, minus this gamma, multiplied with a gradient in that specific, for that specific value. So it means that we need to calculate the gradient, but we have a constant rate here, a constant parameter gamma. And if we now are taking, say, ordinary least squares, just to give you an example. So in ordinary least squares, we know what the gradient looks like. So what we found is that this gradient, the g of n, was now given by this matrix X transpose. And then this was given by the matrix X again, multiplied with beta minus this vector Y. That was the gradient which we found from ordinary least squares. So we have an analytical expression for the gradient. This quantity which you have here is a matrix. Well, let me just wait. This is a matrix. This is again a matrix. This is the vector with the unknown components. And this is the output, or the values which we measure as an output from an experiment, for instance. So here we have an analytical expression for the gradient, but you see that we have to perform this matrix-matrix multiplications. And we are going in the slides now, we're going to see how we can set up such an algorithm. So if you now want to set up the algorithm, what you would need is the following. For ordinary least squares, so you would need to set up, initialize, this is the first thing, by some random value, randomly the different beta values. So beta is a vector, right? So you would now have a beta 0, which is now a vector which contains beta 0 for the first one, beta 1 of 0, and then up to all the parameters you may have, p minus 1. So you would initialize them. And then you would need to define the number of iterations you want to have. You need to set up a matrix X. So you need to define the matrix X, which is normally a matrix of dimensionality n times p, where n is the number of data and p is the number of features. You need to define y, which is the vector of outputs, a vector of length n, the data points we have. And then you need to specify the number of iterations. And then, which we are now just going to call for a variable iteration. And you need also to define a value for the learning rate. So define the parameter gamma. And you could set that one to 0.01, for instance. Then the algorithm would be for I equal 1 to the number of iterations, iter, the final number of iterations. Now, this is a stupid way of doing it, because you would have to put a test on convergence. So let's do this without a convergence test. And then you would calculate gradient. So calculate G, the gradient. When you have the gradient, then you do the update. So do update. And this is normally written like this. Beta is now given by beta minus this parameter gamma times G. Now, you could put in a convergence test. And the convergence test, you could have stop if the absolute value of beta of n plus 1 minus beta of n is smaller than a specific parameter, then you would stop. Or if you reach the maximum number of iterations. So, and you will often see when you're running the codes, I don't know if you remember, you saw all these messages when I run logistic regression before the break. And that simply told me that it hadn't converged with respect to the number of default iterations. So these algorithms in scikit-learn, any library, they have a set of default number of iterations, which you then can increase. So typically it's 50 or 100. And then there is a tolerance, which is this parameter epsilon, which you see here, which is also set in some of the algorithms. So typically this epsilon could be something like, let's say, 10 to the minus 10 or 10 to the minus 8, something similar. But you need to set that. And then you have N4 here. So this is a typical algorithm for doing this recipe. Now, if you can diagonalize the Hessian matrix, so the special thing for ordinary least squares, there is a nice result here, because in that case, the Hessian matrix is given by the transpose of the feature matrix or design matrix times X. So in that case, there is no dependence on the unknown parameters. So I could actually diagonalize this one before I start iterating. If I do logistic regression, this is not the case. And then I would have to diagonalize this one in every single iteration. Because in logistic regression, this matrix is given by X times this matrix W and X, where you have an implicit dependence on beta. So linear regression is actually a very simple case, because then we have no dependence on the unknown parameters. And that means that we could diagonalize this one before we start iterating, and then we would have a value for the unknown parameters immediately. So let's, before we start doing some numerics, let's just see if we can develop some kind of intuition about what is going to happen. So if you now look at the very simple one-dimensional case, and we are now looking at a function, which is a convex function, and many of the functions which we are looking at are convex functions. So if I do ordinary least squares, the second derivative is a positive definite matrix, which means that that is a convex optimization problem. There is a global minimum. So this will be your beta optimal. That is where you find the minimum. And this is the function you want to optimize. This is your C or beta. And then you would start your iteration by some value here, some beta 0. And then depending on the size of your gradient, you may now move down here. So let's just put these marks here. And then depending on the value of this parameter gamma multiplied with the gradient, you may make big steps or small steps. So this gamma defines, because this would now give you gamma times this quantity. So you can now make a certain number of steps. And then after a given number of steps, you get here where you have ideally delta C of beta is equal to 0. Okay. However, you could be unlucky and you could have a case where you have a gamma which is too large. So that means that you would suddenly jump like this, and then you can jump back, and then you can jump away. And what you would typically will see then is that this quantity will just keep growing. And when you run your code, at the end, you will get this message NaN, not a number. So in this case, is gamma too large. In this case, we have gamma ideal. After some steps, we reach the maximum value. But then we could also have a case where this gamma here is now, or let me put that in blue, where we just make many, many small steps and we stop here. So that means that gamma is too small. Now, you will be surprised, and I guess most of you will be negatively surprised, that when we come to things like deep learning methods, like neural networks, we're actually tuning these parameters because we don't know which parameter is the optimal one, which is the one which gives us the best result. So that means often that you will set up a whole set of parameters gamma, and you will try to search among this set of data, the one which gives you the best, let's say, mean squared error, or the best classification. So that means at the end, you're doing a grid search to find the best parameters. And to many, this is a little bit disappointing, as I had a student once who said that when you demystified everything, you took away the black magic of neural networks, right? I think it's important for us, because many of you will actually work with these methods, that we have a deeper understanding of what takes place. Because many of you may even modify these methods and develop new methods. And then it's important to see the pros and the cons. So this learning rate plays a very important role. And I would actually like to come with a kind of small reading recommendation. So in this textbook by Goodfellow et al., which you have a link to, in chapters 8 and chapter 4, there is a good discussion on the different tricks of the trade. So if you can actually download these chapters, and there are lots of small considerations and advices which we don't get time here to cover all of them. But you could now, if you look at a general problem which we face, and if we still stay in one dimension, our problem is that we don't know whether the function has global minima, local minima, or even saddle points. So when we are running the optimization, we could have a function as a function of these parameters beta, which has a global minimum here, there may be a local minimum, then there'd be a saddle point, there could be something like this, and we would typically start the iteration with a value of beta 0. So clearly, if you're here, then here the gradient is also equal to 0. So the gradient of the cost function with respect to beta. But this is normally what we call a saddle point. And we don't want to be there. We could hit this point. So this would be a local minimum. And many of these algorithms are so that if you find a minimum, you just get stuck there. Because the one convergence criterion is that the gradient should become 0. So when you're here, the gradient is 0. But then if you started your beta 0 here, after some iterations, you would actually hit this point here. Or if you're lucky, you may start here, and we may end up here, which is the global minimum. And that's ideally where we want to be. So you see now immediately what is one of the drawbacks with a standard gradient descent is that one, depending on the value of this gamma, the learning rate, it can converge quickly, or it can converge slowly, or it can just lead you far away from the solution. Or you can be stuck in a local minimum, or in a saddle point without you knowing it. Now, for this case, which you see here, it's a very simple thing because you can plot the function. But if you're dealing with neural networks with many hidden layers, you have millions of parameters you're tuning. And that means that you have no idea of what the function looks like. And that's why this kind of randomized searches with stochastic gradient descent comes into play, which we are coming back to. But before we start looking at some examples, let me mention to you a method which is also widely used, which is called the steepest descent, which you may have encountered. And this method is very easy to show, but it is not practical for our purposes. And that's why people often just start playing around with different gamma values. So if you look at what we did here with this kind of approximation where we have a gamma, if you look back here, this is in a way the root of all evil in machine learning. So if you can find efficient ways of updating this one, which reflects the information on the gradients, then like Adam, you can get tons of friends which will cite you. So the method Adam, which we're coming back to, we will discuss that in more detail tomorrow. That has more, as I said, more than 150,000 citations. And that is about updating this quantity here. And there's a lot of research going on in the field. So it sounds like a trivial case, but it is not. So, but before we move on, let me just mention one method which some of you may have heard of, and it's called the steepest descent, which is a method you could apply if you can calculate this Hessian matrix. So if the dimensionality is not too big, then this is something you can do. So when you deal with the cancer data and you do logistic regression, in logistic regression, you have 30 features. So that means that your Hessian matrix is a matrix of dimensionality 30 times 30. And that's something we can calculate. But as soon as you get in the hundreds of features, then this becomes impractical because you have tons of iterations you're doing, and then you would have hundreds of parameters you need to update. And that's where these methods, where you have an approximation to the learning rate kick in. So let's take a quick look at that. The steepest descent, and now I'm looking at a function f. The function f is a scalar, but x is a vector. And we just discussed a form which follows from the Taylor expansion. So this A could now be the Hessian matrix. And then we have the vector transposed x times a vector B, which is known. So x is the unknown, and this is the known quantity. So when they take the derivative, when we want df of x, derivative with respect to x, we want that one to be 0. And that simply gives us a times x minus b, which then leads to the expression which we saw before. So we could take the inverse of a if that's possible, and then we have x immediately. But the typical way to do that is to solve this iteratively. And here's another one of these hidden gems in linear algebra, so which we often don't hear about. So if the matrix A is positive definite or semi-positive definite, then an iterative scheme will converge to the exact value x, irrespective of starting point. That's pretty magic. So you could just start with a random guess for x, and that will always, if the matrix A is a positive definite matrix, it will always converge to the exact value. That's pretty cool. So I'm not showing you these proofs. So what you would do then is to define the error. So let me define residual. So when Francesca comes tomorrow, we are going to fix that screen. B minus a times x. So this is the error which we have. And you could start with a guess. For R0. So you would have an R0 and an X0. So the simplest case could be actually to start with X equal to 0. So you know that you have the exact solution when this residual is 0. when R is 0. That's pretty obvious, right? So if you start with x0 equal to 0, then you have, so if that is a choice, which is fully possible, then you know that this R0 is simply equal to plus B. And B is known. So in general, then, what you have is the following. So in general, what you have is something like an RK plus 1 equal B minus A times XK plus 1. So you're iterating now. And for every iteration, the hope is that R is getting closer and closer to 0. So what we also have in general is that this X of K is now assumed to be given by the previous value, X of K, plus some alpha, which is undetermined, multiplied with the residual. So R of K is the difference between X of K and the new value, multiplied with a constant, which we don't know. So these are just assumptions we make now about what we have. So if I use these two expressions, I can actually rewrite this RK plus 1 in terms of a B, and then I have minus this matrix A, and then I have XK plus alpha of RK, which again, I can rewrite as B minus A times XK. And we know that that is just the residual RK. And then I have minus alpha K times A times R of K. So I can rewrite this R of K plus 1 equal to RK minus alpha K . So probably the recording is not going to be the best one here. Okay, so what we want to find this one to be 0. So if I do that, what we have then is that I have RK equal alpha K times A times RK. Now, alpha K is going to be a scalar. It's just a number. So I multiply from the left with RK transpose. And then I divide by the RK. So what I get then is that alpha of K is equal to RK transpose times RK divided by this RK transpose of A times R of K. So this alpha of K plays the same role as this learning rate. Because when I plug this in, what I can find then is that method, but it's useful only when you can calculate this ratio here. So if you go back a little bit to what I put up earlier, when I did this Taylor expansion, we found that when I did this Taylor expansion, I found a relation which is pretty similar. So this R of K is the same as a gradient. And this matrix A we put up is the same as a Hessian matrix. So that means that the relation which you see here plays the same role as what we had earlier. So this kind of expression here is similar to what we get from a steepest descent method. And all of these methods function if you can calculate the Hessian matrix, which in general is not the case. So let's look at some examples and try to go through them here by looking at the Jupyter notebook. So let's just switch. So I'm going to skip some of these definition of what is a convex function, because this is probably something you have seen before. And this is just a brief reminder on Newton's method. But I just wanted to show you some of the examples and you will actually find examples of the steepest descent and some of the standard methods, which all require that you can calculate the second derivative. But let's now go back to some of the first slides and the first topics we went through. And what I'm going to do now is to set up a simple function, which is just a first order polynomial. And we have some x values, which are just set up by a random distribution between 0 and 1, multiplied by 2. So that gives you a number between 0 and 2. And this is the function. This is the data I want to set up. And you can then set up the, if we have 100 points, this is my design matrix when I'm now fitting it with the intercept and the first order polynomial. So this is the way the design matrix looks like. And then I know that my cost function is simply given by this function here. I have two parameters, beta 0 and beta 1. And then with that, I can now calculate my derivatives, which are pretty straightforward. And the general mathematical expression is given by this term here, because I'm starting with a function which has the data set 1 over n here. And then I can also calculate the Hessian matrix, the second derivative. So this is simply given in terms of these different derivatives here. Let me just increase the fonts a little bit. Can you see well in the back? Is it okay? So these are just expressions. I'm just putting them up more for pedagogical reasons. And then we can set up a simple program. And this is a stupid program because I didn't put in a convergence test, which you should do when you run the things in a more serious way. So what you have here is a comparison between my learning rate now, where I actually use the Hessian matrix and I calculate the learning rate, which is given. So I'm calculating that one just to see what it looks like. And I put that one to be 1 divided by the max eigenvalue. So let's run through this example. So what you see here, this is standard linear regression with ordinary least squares. In principle, I should take the pseudo-inverse in case there are dependencies. We should do that. I'm setting up the Hessian matrix, which for ordinary least squares is independent on the optimal parameters beta. My beta value is randomized initially, the setup as a random value. And then I calculate my gradient. And now you have to, if you look at what you have here, this is a full gradient. So if X is a matrix of dimension 1000 times 1000, this guy here takes 1000 cubed floating point operations. So matrix multiplication is expensive. So if you have a square matrix of dimension n times n, and n is 1000, then it takes 1000 cubed floating point operations, which is a lot. This is also one of the reasons why one normally splits the calculation of gradients in smaller batches. These are called mini batches, and it's used in stochastic gradient descent. So here we are calculating the full gradient. And if you have lots of data, this becomes computationally expensive, especially if you have many beta values. So this is your beta, and here we just update it. And if I then plot it, what you would see here is, let's take away the noise. You see first, this is my matrix inversion, ordinary squares, and you see that I get the same result here. So I now tuned the value of the learning rate to be optimal. But if I now put it to 0.1, suppose we do 0.5. Let's try that. What is this? 10 to the minus, 10 to the plus 85. So if we go back to the drawing which we made just a while ago, so let's just take a look at that. So that would be a case, oops, why didn't this come up here? So if you look back at the image which we had just some few minutes ago, this is a case where I have a very large learning rate. And then I jump down here, I jump here, and then I jump out. So this is a process which doesn't converge. And it's a typical example of a learning rate which is too large. And what you will see then, when you run this for neural networks, where you choose a grid of values, and the values of the learning rate can range from 10 to the minus 5 to 1, you would typically see that in the sense that some results just go crazy. They're just becoming meaningless. You have, for instance, a mean squared error, which can become very large. Or if you do a classification problem, you get the 0 correctly classified events. So this is us doing that. In the previous case, we had an optimal learning rate, which was tuned by the eigenvalues of the Hessian matrix, because I could diagonalize it. Now, if I make it too small, let's try that. Let's make a very small learning rate. And then you will see immediately the effects here. So let's go back to the Jupyter Notebook. And what we're going to do now is simply to put that one to, let's just take it 0.001, for instance. And now I have a stupidly large number of iterations. I mean, when you run this with neural networks, 1,000 iterations is actually a huge number if you have millions of parameters. So you would often try to reduce that one because that means much more floating point operations. So anything you do in machine learning is you setting the balance between the number of floating point operations you're willing to spend and the precision of the results. And you have to judge then what is an optimal result. If we do this, you see now this is what we should get. Oops, let's. So this is the value we should get, which you see here from matrix inversion. And now when the learning rate is too small, we're not even near the correct values. So these are all kinds of examples which you can play around a little bit with and see what happens when you play around with the different learning rates. And you can replace ordinary least squares like we have here with the ridge regression. And here I'm actually using also the stochastic gradient descent method. You can do that with ridge. And in ridge regression, we have a penalization parameter or shrinkage parameter, as we called it. And then when you take the derivative, and this is always useful to do that by hand if you can, then you have a parameter here, lambda, which you have to tune in order to eventually get a better mean squared error. And this is the gradient which you have to plug in. So the only change now is that your Hessian matrix will always be positive definite for this case, because this matrix can be semi-positive definite, but adding a constant along the diagonal will always lead to a positive definite matrix. So this is always a convex optimization problem. And in this case as well, you can just rerun everything by simply adding this lambda term along the diagonals, and then just rerun. And we could actually take away the randomness in the data, and then we will actually get a perfect fit here. And you see that the results, we started with 4 and 3, and we are getting 4 and 3 here, basically to numerical, almost to the kind of precision we want. We can now increase, if we now increase the iterations. Oops, that should actually not have been, no, wait. Oh yeah, no, there's a reason for that. I forgot that. The reason for that is that we have a value for this parameter lambda. So if we now look at this parameter lambda, which we had, if we now put that one to 0, because this changes the result from ordinary least squares, and now we get 4, 3, and 4, 3. So with the region regression, we don't get the same result as the best result in that case for this polynomial fit is ordinary least squares. And you will see that in the first project. If you use this vanilla data, that ordinary least squares is going to give you better results for polynomial fitting when you take away noise. So if we now summarize this, so tomorrow, what I wanted to discuss in a regular lecture is what's called stochastic gradient descent. And I'm going also to discuss this momentum-based methods. But if you now look at the kind of summary here, these algorithms here, it's able to find the minimum function. It normally converges to a local minimum or a global minimum. It can lead to poor performance because we often have a very complicated function. You saw that it's very sensitive to the initial conditions. It's very sensitive to the learning rates. And they're actually computationally expensive to calculate for large data sets because we are calculating the full gradient. It's very sensitive to the learning rates. And another thing which happens with these methods, this is a little bit irritating actually. So another thing which happens with these methods, since you use a constant learning rate with no knowledge about the gradients and the second derivative, it will have the same change in all spatial directions. So if you have 100 values of beta you want to optimize, you're going to get the same gamma or learning rate value for all the gradients. So some of the gradients can be smaller, some of them can be larger, but they are multiplied by the same factor. And that can often lead to very slow convergence. So these methods are extremely, as you saw, they're extremely simple to implement. And in some cases, people use them as a starting point. If you're a little bit unsure about these methods, you would actually use them as a starting point when calculating different gradients because they're so easy to implement. And also, tomorrow, when we will be discussing gradient descent together with automatic differentiation, this is a very useful way to start benchmarking your program. So you're going to meet a function or a Python library, which is called automatic gradients or autograd. And this allows you to calculate gradients to numerical precision without having to actually code derivatives yourself. So that sounds like heaven almost. And it gives you also much more flexibility in these optimization parts because then you can actually just bring in new cost functions and you don't need to sit down and write down all the derivatives of this function. So when you're developing a numerical project, there is another aspect which many people tend to forget. So when you calculate the gradients by paper and pencil, you can program a very efficient expression. But that can take some time. When you use automatic differentiation as an algorithm, that brings an overhead when you calculate. So computational time increases. But your total time is not only computational time, It is development time plus computational time. So if it takes you a month to develop all the analytical expression, and autograd is just a call in one line to a function you have, and that increases your program with some few seconds in runtime, then clearly you would use automatic differentiation instead of spending a month on finding out all the equations by hand. And I used to say it's fun to calculate derivatives, but it doesn't give you a deep insight, does it? We know how to calculate derivatives. And we know it's so easy to make errors when we have the analytical expression and translate that into code. So tomorrow, we're also going to discuss automatic differentiation, and we are going to look at stochastic gradient descent, which is a way to hinder that we can be stuck in global minima or saddle points. And these are the methods which are normally used in this fine-tuning. So today served as a kind of, how to say, to give you the big picture of where the problems in machine learning are. Because at the end, we want to find the optimal parameters by calculating derivatives or gradients. And that's a bottleneck. That's really, I mean, it sounds very simple, but it is the bottleneck in all of machine learning. Every algorithm has an optimization part. Whether you do neural networks, convolutional neural networks, recurrent ones, you're using generative methods, you're calculating derivatives of functions. And you're optimizing. Should we take a small break and then go back to the project? Because I wanted to discuss that a little bit with you guys. If that sounds okay. Let's just do 10, 15 minutes.